Tim, welcome.
Cool. Double checking this works. All right, sound good? Okay, so maybe a little hot. How's that? Okay. So Wasm all the way down is my talk. Try to adjust that a little. Like I said, I'm Christopher Swenson. Just a little bit about me. He, him. Currently at Microsoft, previously at a bunch of places. I am a huge fan in general of programming languages, cryptography, math, sorting algorithms. I love all that nerdy nerd stuff. I do have a book. I'm working on making a new revision of it called Modern Cryptanalysis. I'm on Mastodon, and theoretically I have a YouTube channel. It has 2 videos on it. You should encourage me to make more because they're a lot of fun. You know, only so much time in the day because I spend so much of my time thinking about Wasm. So the motivation for this is about 6 months ago, I was doing a hack week at HashiCorp. This is one of my favorite things that I ever did at HashiCorp was, you know, we would every now and then get a whole week to just work on whatever we wanted. And I was like, what if we took the application that I work on, which is called Vault, and turned it into a Wasm application so that it could be embedded in the browser. So that like Vault is notoriously difficult to get configured and working and interact with it. So I was like, it'd be really great if we could like embed it into the tutorials and you could just like play with it there without booting up your command line environment and all that kind of stuff. And so I got it to work. It took a couple days of effort because it really did not want to get shoved into Wasm. So that was a lot of fun. Go has really powerful like built-in support for putting your code into Wasm and JavaScript as like a first-class target these days. And so after that, I kind of decided I wanted to dig a little bit further into Wasm and figure out like what's all going on here. I learned a little bit about it in this project. I wanted to learn more, and I thought it'd be really fun to write my own Wasm interpreter in Python like you do. So Wasm, just to give you a little bit of an overview, who here is familiar with Wasm or WebAssembly? So a fair chunk of people. So WebAssembly is, or I will say Wasm mostly because it's fun. It is a specification for basically a portable 32-bit machine, like a virtual machine sort of. It is designed, I think I'm quoting from the spec, for efficient execution and compact representation. And it's a successor to ASM.js, which kind of did a similar thing. It wasn't really quite standardized. They standardized it a few years ago. It's been really popular for running stuff in your browser that was never meant to run in a browser. I will say sometimes interpreter or runtime interchangeably. In Wasm, the terminology is runtime for the thing that actually runs your Wasm code. And it's very similar to like a virtual machine. It's basically a self-contained little box that runs code that's written in Wasm binary, essentially. Generally, whenever you compile stuff to Wasm, it's meant to be run in a sandbox in a web browser so that you could take your arbitrary C or whatever programs, run them in your browser. So keep that in mind as we're going through, because we're definitely not going to be doing that, because web browsers are just less fun. So some more stuff about Wasm. This talk is going to be a lot about Wasm. So some really cool things about Wasm that I like. There's a very strict separation between code, variables, memory, the call stack, and the data stack, meaning these are all completely separate concepts even, and they don't really interact in the way they do in most like machines and assembly languages, where those are kind of like on x86, which is most processors, those are all sort of the same thing. Like they all live in one shared space and they commingle. And also variables being like their own first-class citizens in this is really strange for a virtual machine. Most times in programming languages or virtual machines, like you don't really have variables as a concept. Like that's sort of like an abstraction for us humans, but they actually exist in the Wasm execution format. One really cool thing is they have really rich block semantics. I'll go through some examples of that. It's really great for its tight integration with JavaScript. It's meant to interact with the browser really easily. It's very nicely sandboxed, so it's meant so that you can take your very untrusted C code, run it in your browser, and not have to worry about your browser crashing, hopefully. And it's very Risk-like, and by that I mean every operation is sort of like only some operations operate on memory, and most of them just operate on their operands, and everything is nice and orthogonal and easy to compose. So kind of Risk-like in that manner, although not strictly speaking Risk. Some of the sort of misfeatures of Wasm are also some of the features. So it has a very flat memory model, and the downside to that is everything is like 32 bits, so there's only 4 gigabytes of memory, and that is all there is. Like, you're not going to be able to use more than 4 gigabytes of memory. I think some of the newer specifications they're coming up with might be trying to address this by having segmented memory, but in the current V1 of Wasm, one big flat space of memory. The semantics are very JavaScript-y of it, so it's really great at interacting with JavaScript, but like if you're thinking about, say, porting your Go code or your Python code to it, it doesn't quite match up as well because like a lot of these concepts just don't mash as well. Like I did say earlier that there was sort of this call stack and this data stack. I can't point because my laser's broken. But there's actually technically no data stack in this, so, and there's not really even much of a call stack to speak of. I'll kind of explain what I mean by there being one and there not being one in a second, but technically when it's running there is no stack. So that means that you have to sort of emulate the stack yourself in any language like Python or whatever that requires one. Hence, there being no stack, there's no frame pointers, no instruction pointers, no reflection or introspection really at all in it. Like if you are a piece of Wasm code, you can't really see what you're doing. You can't really even know where you are. You can't know what functions are out there. Like you get a very isolated view of what's going on. Great for security. It's kind of a weird model though for programming. And that tight integration with JavaScript, again, that's kind of a good and a bad thing. It means that if you're trying to work outside of a web browser where you may not have a JavaScript interpreter, you may just be really screwed. Spoiler alert. So my plan was, I was like, okay, I'm writing a Python interpreter for Wasm. I'm going to maybe try to write some imports. So the virtual machine sandbox itself, like I say here, it's a specification for a 32-bit instruction set. It by itself has no way to interact with the world outside of its sandbox. It cannot talk to your browser. It cannot talk to the network. It cannot talk to the disk or to the screen or anything. It just runs in its own little world, and you kind of pipe in some functions to help it communicate with the DOM or the browser or your graphics or something along those lines. So I wanted to see, I assumed that maybe I wouldn't need a lot of those ways to pipe in since I just want to run maybe like some simple Python programs. And I want to run maybe PyOdide. PyOdide. It was mentioned in a talk earlier, but it's basically CPython compiled to Wasm using something called mscripton. And there may be a couple other options, but that's like the main way that you can like boot up Python in a browser and play with it. And then my plan is to like recurse that, so now I can take my Python Wasm interpreter and run it in itself. All right, that's the plan. But spoiler alert, I didn't actually get that finished. So this is the downside of conference-driven development that you don't talk about, is that sometimes you spend like 6 months working on a talk, and then you're like, oh yeah, by the time this conference rolls around, I'll have made the magic happen. And sometimes the magic fails you. So this talk is about failed magic in that sense. So I did spend a long time working on this, and I did get a working Wasm interpreter runtime working, but those like little pesky things I mentioned where you have those imports that come in and help you interact with the world, it turns out those are a total nightmare to port over. So I'll talk a little bit more about that. And I'm going to talk a little bit more about Wasm now, because Wasm is really cool, and it's really neat to, I think, learn about these pieces, and I'll explain exactly why this failed. So how to write a Wasm interpreter the Swenson way. This is the Swenson standard method for writing a compiler or interpreter, and it's to just, don't bother reading the specification, by the way. Like maybe a little bit of it, but just skim that over. That can't be that important. You just pipe in your bytes. You start recursively, like just parsing every single piece you get. You don't want to take the time to actually write classes, so you just use a bunch of name tuples. Name tuples are really cool for like quickly prototyping out your code. You just sort of guess at what every piece you do goes on, and then you realize that nothing's working, and so then you reluctantly go back and you actually read the spec a little bit more deeply, and you realize you screwed up really badly, and you have to rewrite everything from scratch because the semantics are a lot weirder than you ever expected. Then you get that working, and then you realize that there's a bunch of work left that you didn't anticipate, which is how we are. And I have to write some Python code because it's a Python conference. So this is sort of this is the actual beginning of my parser. The details don't super matter a lot, but there's nothing magical going on. I'm basically read the binary, check the signature, and then start recursively parsing out the sections. And then if my laser pointer worked, I could show, like, as I'm kind of going through here, I'm reading each custom section itself and like basically just parsing all the big chunks of it, and then I can start executing. So here we are. Like, what does Wasm look like, though? So we've talked a lot about what Wasm is, but like, what does it like look like? Because that's how I think about things and try to understand them. So even though I said there's no stack, but there sort of is a stack, you think about it in terms of a stack, but in practice, we'll actually erase that later on. So you think about it as a stack. So these are 3 opcodes in WebAssembly. The const opcode pushes something onto the stack. So you have a 1 and a 2, and then sub pops those 2 things off the stack, subtracts them, and puts the result back. And this is sort of the basic like operation of how a stack-based assembly language like Wasm kind of does it. In reality, what it'll do, instead of actually building a stack, is you like assign those to registers, and you like cleverly rewrite it as you go along. But conceptually, you can consider it as the stack, and everything is still correct. But in practice, you typically don't do that for complicated reasons. So as we continue our Python, like this is the implementation of those operands. I went ahead and just made a stack anyways for conceptual purposes. But if you see a const, then you push something onto a stack with append. And if you need to subtract 2 things, for instance, you pop one off, pop the other one off, and then push onto it the result of adding them together. There's some functions that help me deal with signs and stuff like that. Also, a fun fact about WebAssembly, everything is typed. Like even your the locations of your variables and stuff are all strictly typed. It's just that there's only 4 types. There are 32-bit integer, 32-bit float, 64-bit integer, 64-bit float, and that's it. Those are all your types, so all of your stuff deals with those types, which is kind of fun because it also means you can check your work, because if you pop something off the stack and you expect it to be a 32-bit integer, but it's really a 64-bit float, you know that you have a bug. So let's look at something more complicated. This is WAT, WebAssembly text format, well named in this case. So this is a function. So just like any other kind of language or environment, we break things down into functions. And then if you want to think about the Python code as we're going along, this is like defining like an unnamed function, or maybe it's named f, that returns 100 if 1 minus 2 is equal to 0. Otherwise, it returns 200. So in assembly, this looks like push 1, push 2, subtract, check if it's equal to 0. So that's just this operation there. And then we enter into this if block. And if takes a look at whatever was on the top of the stack, which is that comparison. And then it has a result. This if block can return something, which makes sense. Like in Python, you can think about this is a block and it returns something. It's like an expression. And then we have constant 100 if it was true, constant 200 if it was false. So it literally is just that there, implemented in this sort of stack-based way. Not too bad. Nope. There we go. In general, those concepts of blocks are really fascinating. Almost everything in WebAssembly turns into blocks. So a block is really just a group of instructions. It can accept parameters in addition to returning values. Very rarely do we actually see it accept parameters. But you could think about it like if you had a lambda expression like that took a parameter. Like that kind of makes some sense, like even in Python. But it often uses to return like a value so that you could have like that if-else kind of format. The if statement is just another block. And so another key feature is that if you call break or branch, and then give it the block name, it will immediately exit the block and return whatever value. Now there's a tricky bit here. So if you look at this sort of block, we are pushing a value 1. We're actually not checking a condition there. We're just checking whatever's on the stack, which will be 1, which is true. And then if that's true, then we push 1024, we push 123, and then we break out of this block, returning the last thing on the stack. And otherwise, we push this onto the stack. So there's some weird things going on here. The result there, so this block is returning a result, like I said, but we have some extra stuff on the stack, like that 1024 was there. So this is the difference between WebAssembly and almost every other assembly language or other language, is that if you have other stuff on your stack, whenever you break out of it, you actually just throw all that away. And it's sort of the responsibility of the branch instruction to know both the contents of the stack where it's going to, does it need to return a result? And if it does, it needs to grab that last value off the stack to return it, throw everything else away. No matter how many levels deep we are, it has to like understand where it is. Like if you're 10 blocks deep, you branch out 5 of them, you have to like look at everything in between to figure out how many like things you need to return and whatnot. It gets really, really messy. Like it looks very simple, and if you were like me, just kind of blindly going through and implementing all the instructions, you wouldn't realize that, because like usually like a branch or a jump instruction, they just do what they say. They just jump somewhere. Like, but this one actually has to like deeply manipulate the stack, understand the return type of where you're going to, or the parameter type of where you're going to, and deal with that. And you might think, oh, well, then maybe I should have just read the spec. And luckily, there is a spec that tells you in exact detail how a branch and how a block statement works. But unfortunately, it looks like this. And I'm not going to explain all of it. I do sort of understand it, but it's like, and by the way, when you read through the WebAssembly, like execution, I think this is in the execution section or something, it's like, oh, it just expects you to understand all of this, doesn't define any of these terms. It just like, it's like, oh yes, of course you've all been to grad school and taken graduate level programming language classes, and like clearly are like, yes, let the label, you know, whose arity is n, and the continuation is the end of the block, and then blah, blah, blah. Like, it's like, really? Like, no explanation for any of this. If you like read it really slowly, you can kind of see it does kind of what I said earlier in a very complicated way. But don't worry, I'm not going to go through that anymore. We can take that away. It's quite horrible, but it is extremely precise, which that part's nice, but it doesn't really help you, I think, understand what's going on. To make matters worse, there's loops. So a loop is basically a special block. It is, in fact, exactly a block, except for when you branch to it, you go to the beginning instead of the end. Otherwise, a loop actually never loops automatically. A loop will always break out at the end unless you branch back to it. So this is a simple loop that really just counts down from 4. So we push 4 here. This loop takes a parameter, so that means it eats the first value here, and then it will return something as well. Maybe there's some checks here that subtract and stuff like that, and then at the end it will maybe branch back if it gets to some particular value that it's looking for, t. I'm not going to go into the details here, but like this basically, you can see when it branches here, it's actually going to absorb maybe a value to loop back into itself, so that this local.getT will be passed back as a parameter until it breaks out of the loop here at the very end, and then the value $A will get returned from the loop. So loops can accept values, return values. It gets really complicated, especially as they get, like I said, nested, where you might have multiple layers of accepting parameters and returning results, and you can branch from, you know, any one of the inner ones all the way back out again, and the branch instruction needs to just magically have knowledge of all of those layers so that it can pop them all off the stack, clean up the stack. Yeah, again, that took me quite a while, like like many weeks to like really grasp and understand, because it wasn't, again, it was not clear from this spec to me that you know, that the branch instruction will be magically cleaning up the stack and has to magically know where it's branching back to. Like, it's very subtle. Okay, so not only was the blocks and the loops that really got me, they're a lot of fun to like play around and think with once you kind of get it. But now, when we actually get to running something like CPython, it's not just a matter of running the instructions and running the loops and running the branches. There's also, it turns out, the way PyOdide compiles with Emscripten, it like expects you to implement roughly 1,300 functions along with it in your, like, wherever your native like environment is. Usually these are all written in JavaScript, and they've already have like blanket implementations of them meant to run in the browser, because, you know, they did this once a decade ago and they just keep reusing those. So they're like, oh, of course you have, you know, all this JavaScript around to just like load into your browser. Well, I'm writing a brand new thing from Python and Scratch. There's no JavaScript environment to run in, so I have to implement all of these functions by hand, and my hands got tired. There's just a lot of them, and a lot of them are also incredibly undocumented on what they do. They just have names like invoke_i, and then invoke_I. Like, literally those are names. I think that means how many integers they take as parameters. But again, these are all like undocumented. So the stuff that Emscripten gives you is pretty undocumented on how to run it. I did eventually get it mostly working with initializing. Like, I can give a quick little demo of what little does work.
What could possibly go wrong?
So here's it just parsing stuff. You're mostly just going to see an error message. But it does actually go through, executes a bunch of assembly. It's now applying like data relocation. So it's basically like loading everything up into RAM. I purposely slowed it down so that you can kind of see it. And eventually it crashes because something in the initialization failed right around, let's see here. Yeah, so this is the call stack here. It's like a bunch of C++ mscriptum initialization, like functions that may or may not exist that it's trying to call. And then it tries to access memory that's too far out, which means there was a bug somewhere. Yeah, so anyways, it does get like partially through initialization, but I kept hitting all these functions I needed to implement. I got some of them implemented, and yeah, it was just a whole lot. The complex branching slowed things down, so those complex branches and loops and blocks, it took me a while to really wrap my head around how to implement those. And then there really honestly aren't a lot of great debugging tools that I found. So in order to continue this, I think I'll probably write a good debugger, at least one that works for me, so that I can kind of understand what's going on inside my Wasm code. Let's see here. Yeah. So what went right? I wrote a very nice slow Wasm runtime in Python. Works pretty well, honestly. I learned a lot about PyOdide, and then I lived to regret my choice of PyOdide. I think if I were going to do this again, I probably would target something like MicroPython, because I think MicroPython will be powerful enough to run my Python code itself and recurse. I did look at something like GPython, which is Python implemented in Go, but unfortunately, it doesn't implement enough of the standard library to be super useful. And so then the other option is to write my own Python interpreter in something like Go that has an easier Wasm target, and then use that to bootstrap itself, and do this. This way I can avoid all this mscriptum stuff that I need to port over. But so obviously the solution is to write my own Python interpreter, as well as the Wasm interpreter, and then combine them. But that'll be the next step. Yeah, that is my talk. Maybe stay tuned for more Wasm wackiness as I get this to work. Code is available on Swenson/PyWasm. I'm available for talk after this or questions. Yeah.